Hello everyone, this is Jiahui Gen, currently a postdoc researcher from the MBZAI in Abu Dhabi. My research focuses on the trustworthy AI system by addressing the utility and the safety. Thank you for the opportunity to share my recent research in cybersecurity. This presentation highlights three of my most relevant work in cybersecurity, especially AI security and privacy. The first one is on jailbreaking defense in multimodal large language models. It is recently accepted by Triple AI alignment check this year. And the second one, first on the privacy attack in large language model fine-tuning technique. It has been recently accepted by the New RIPS dataset and the benchmarks track. The third one addresses the data recovery attack and defenses in federated learning. It was published last year in IEEE Transactions on Big Data. Together, these works contribute to advancing the security and the privacy of AI systems and their applications. Our first work began with the observation that the vision language model are more prone to jailbreak attacks. When a model responds to a malicious query that it should have rejected or considered the model was successfully attacked. As shown in the image, the model initially rejects unsafe textual input, but complies with unsafe textual visual input. To investigate this phenomenon, we designed a systematic study to uncover the underlying reasons. Our experiment was based on a hypothesis that the model's internal activation could reverse the input types. Here we refer safe and unsafe queries. Using two independent text-only datasets and one multimodal dataset, we conduct a series of experiments. Figure 1 shows the internal activation realization with TSNE algorithm. The activation distribution for text and the textual visual input consistently exceed the significant differences. So this finding suggests that the safety alignment of the large language models embedded within the vision language models lack robustness in handling the distribution discrepancies between the unimodal and multimodal input. This misalignment potentially exposes the model to vulnerabilities, underscoring the need for more robust safety mechanisms. In this slide, we introduce the process of the performing revision as well as how to extract the vectors required for this revision process. Especially, we designed two types of activation revision method. The first is layer level revision, which is applied after the NLP layers. And the second is the head level revision, which targets at the individual heads within the multi-head attention. For calculation of the revision vectors, a straightforward approach is to leverage the constructive information between the positive and negative samples. To achieve this, we propose two methods, probe weight direction and the mass mean shift. Especially, the probe weight direction identifies the optimal separating hyperplane between the positive and the negative samples, with the revision vector oriented perpendicular to this direction. The mass mean shift method computes the activation cluster centers for safe and unsafe responses. The revision vector is then defined as the pointing from the center of the unsafe response cluster to the center of the safe response cluster. The first table summarizes our comprehensive result, exploring the impact of using different data types to extract the revision vectors, various calculation methods, and the revision positions. We found that the activation revision method using multi-response as a head level with MMS outperforms the fine-tuning approach. Especially, head-level revision strikes a better balance between the safety and helpfulness compared to the layer-level revision. Moreover, the multi-response proves more efficient for revision vectors than the text response and multi-instruction, while MMS outperforms PWD as a calculation method. The second part of the result shows how different layers, height, and the strength parameters alpha affect the model of the performance. Our results indicate that with the same alpha, the deeper layers shows a greater impact across various attack tasks. Additionally, the choice of the revision layer and the strength alpha key to balancing the trade-off between the safety and the helpfulness, offering insights to optimize model alignment. Thank you. For this work, let me first introduce the background of this work. The pipeline of the training large language models often allows two main steps: pre-training and adaptation tuning. While this process allows us to adapt pre-trained models to a specific domain, it unfortunately introduces privacy risk. For example, in the financial dataset, the models inevitably reveal sensitive details, such as the CEO's opinions or internal data classifications. Similarly, private user information like emails, names can be leaked from adapted models, demonstrating a critical privacy risk. To address these risks, we propose Priv Auditor, a benchmarking framework designed to evaluate privacy vulnerabilities in large language model adaptation techniques. Let me walk you through the main features. First, it evaluates a wide range of adaptation texts with diverse characteristics, ensuring a comprehensive coverage of the common method used in practice. Second, it assesses privacy risks across varied domain data modalities, including financial dataset, corporate climate policy engagement, and static text-to-SQL dataset. Third, it supports different pre-trained model architectures. The fourth, it integrates representative attack methods that simulate real-world privacy threats, including particularly 7 types of membership influence attacks. By systematically evaluating adaptation techniques, it helps us to identify privacy vulnerabilities and propose defense to ensure sensitive data remains protected. Our experimental results address 3 key research questions related to the privacy vulnerability in large language model adaptation. First question is data vulnerability to leakages? Our results show that the distributional difference generally exists between the member and non-member data. Strong MIA attacks effectively detect data used for the language model adaptation, and language models used for structured data demonstrate greater robustness against the MIA attacks. The second research question is, do different adaptation techniques vary in their downstream privacy vulnerability? We find that, as shown in the table, different adaptation techniques may cause systematically vulnerability difference due to their associated attack surfaces, and more trainable parameters lead to higher data membership leakage risk. The third question is, what factors potentially affect privacy vulnerability in large language model adaptation? We find, first, utilizing more data makes the attacks less effective. And for the second graph, find increasing the number of the iterations generally enhance the effectiveness of the attacks on the target models. On the third graph, we find that large language models tend to increase downstream privacy vulnerability, at the same time increase model utility after the adaptation. So this is a kind of trade-off. This work is about improved gradient information attacks and defenses in federated learning. So federated learning is a distribution machine learning framework designed to enhance the privacy protection. So in this approach, a federated server trains a global model by aggregating data characteristics from multiple nodes. Crucially, node and the servers share the model weights or gradients rather than their private data. A natural question arises. So is it possible to reconstruct training data and labels from the shared information? This question has been explored in prior studies, with such attacks being categorized as gradient inversion attacks. The underlying mechanism of this attack is based on the principle that data and model weights can determine the gradient. So conversely, the model weights and gradient can reveal the data. This attack leverages the gradient matching to reconstruct the data, especially when a victim model computes the gradient information based on its training data and labels, and it shares the gradients to the server. If an attack gains access to this gradient, they can initiate an attack. The attacker begins by creating random noisy images and labels as seen in this picture, and then calculates their corresponding dummy gradients. They then attempt to minimize the distance between different gradients through iterative optimizing of the dummy images and labels. Over iterations, the trained images and the labels can be effectively reconstructed. However, this method has notable limitations. It is challenging to optimize both the images and their labels simultaneously as the batch size increases. Additionally, the approach fails to be effective when the batch contains data with duplicate labels, limiting its applicability in real-world federated learning settings. In this work, we propose a novel attack framework capable of tackling both feed SGD and feed average algorithm. And we provide a mathematical proof demonstrating that the duplicate labels within a batch can be directly inferred. As shown in the left, our reconstruction functions incorporate a gradient matching loss and auxiliary regularization for fidelity, enhance the quality of the restored images. Additionally, we introduce a one-shot batch label inference method, and our experimental results confirm that the correct inferred labels significantly improves the image restoration quality. Figure 1 illustrates the image results, the restoration results, where there are no duplicate labels in a batch. The top two rows display the restored images, while the last two rows show the ground truth. The middle part of this slide shows the result and the algorithm on feeder average method, and the right part we present the result when there are duplicate labels within a batch. The top two rows are the result from other methods. The middle two rows are our results, and the last two rows represent the ground truth. Our conclusion is that maintaining duplicate labels within the same batch and increasing the local training epochs are effective defense strategies against such attacks. That's all for this presentation. Thank you.